Hello everyone, and welcome to our second distraction of this video series, where I'm going to waste 20 minutes or a half hour, maybe more, we'll see, of your time. And instead of talking about whatever's next in Kashiwara and Shapira, I'm going to tell you something that I think is interesting about what we've been learning. And today, I'm going to tell you about one of my favorite examples of an interesting topological space, which is called a solenoid. And also, I'll probably say some words about the p-adic numbers while I'm at it because it's sort of relevant. Um, and these are sort of examples of interesting limits and colimits that we're going to take a look at as sort of our final example, but I wanted to sort of upgrade it from just an example to sort of give it a video of its own because it really just feels like something that's so strange, at least at first, that it warrants taking the time to discuss it. So the prototype of our example, the prototypical thing that we're going to do is follow sort of the recipe for discussing limits that we've been following. I'm not going to prove you any super sophisticated theorems, but just like last time, I want to start with a sort of simple category that I think of as a blank diagram, and then we're going to think about what kind of functors we're going to get out of that category into some other category, and then think about limits. And our prototypical category for this example is going to be the natural numbers themselves, where the objects are, of course, just the numbers. And then there's a morphism between two natural numbers, a unique morphism, which I'll just call star. Actually, I'll even go further. I'm going to call it this symbol, the less than symbol, if and only if I is actually less than j, and otherwise it'll be empty. So this is just a poset basically on n. Or just think of n as a partially ordered set where the morphisms go just like with the numbers, and this is our category. And then, just like with every other example, we're going to think about limits of such functors out of n into some other category. If I have such a functor, then I will call the limit the forward limit. This will be called the direct limit. And if it goes backwards, then this is the inverse limit. Wow, can't read that at all. The inverse limit. This is nice. The terminology is at least sort of good here. It's backwards from what you might expect with like limits and colimits. Like the direct limit is a colimit and the inverse limit is a limit. But at least it matches up with the notation where the direct limit points forward and the inverse limit points backwards. It's a little annoying that there's this sort of mismatch somewhere, but this is why I've tried to use inductive or injective terms for the limit and the projective limit, just to sort of avoid this confusion altogether. This is just sort of life when one is doing category theory. So what I want to do is show you how this idea of a solenoid, what it is, how you construct it. It's going to be constructed as a particular colimit. In particular, we'll have this direct limit. And then we're going to sort of see how this corresponds to certain algebraic constructions, and hopefully I'll be able to draw you pictures to sort of show you what's going on, and we'll get to test my artistry skills in this video. Okay, so what's a solenoid? Well, a solenoid is an object that we construct using an iterative process, since it's going to be a colimit. And remember that if I have this chain of morphisms here, like so, right? Sorry, it's a colimit, so it goes the other way. So we're looking for functors that run the other direction. So I have maps that look like this after reversing the arrows. And then the limit, if it exists, is this object that sort of lies over all of these things. So I drew it underneath, but I said over. I don't know why I did that. But the point is that it's this universal thing that sort of maps down to all of them. And so the way that you should think about this is if this universal object exists, then it's sort of a limit of what you might think of as partial colimits, where what's going on is at every step, I have this object that projects to each factor, and each higher factor is sort of like a better approximation of what's going on. That's not just, how do I say this? That's not just like a slogan, that's actually how I'm going to construct solenoids. I'm not 100% sure that that example or that slogan is completely right in full generality, but it's definitely right for this construction, so we're going to run with it. So the construction that we're going to do is we're going to start with our circle. A circle is the simplest example. There are more general constructions of things that also call themselves solenoids. Like I'll let somebody who cares try to generalize this to its greatest degree of generality. But for now, our base object will just be a circle. And what we do is we look at a covering space of this circle given by the 2-to-1 covering map. So what I do is I then have this other thing that lies above it, which sort of looks like this. It's not a very good drawing. Let's try to do it a little better. There we go. Sort of looks like this. And this is also a circle. It's sort of a circle that goes around twice, so geometrically it would be a bigger circle. But topologically, it's just a covering map from a circle to itself. There's no such thing as a bigger circle. What the map does is it's the angle doubling map. So it takes any point, and we send e to the, let's see, e to the theta I, e to the 2 theta I, regarding these as unit complex numbers. Or if you want to think of it just like, theta maps to 2 theta, that's fine too. So what's going on here then? We have this map of circles, and we know from topology that there's this correspondence between the covering spaces of a given space and their fundamental groups, and the subgroups of their fundamental groups. So pi1 of S1, hopefully if you're watching this video, you know that that's isomorphic to Z. And this group up here, well, it's also a circle, so it's also a circle, but the map is the map that sends 1 to 2. In other words, is the doubling map. So we think of the image of this map lying in here as actually being just the coset 2Z, like so. So the way that you want to think about this then is, or at least what you want to think about this construction, is we're going to repeat this construction. And we're going to iterate this to create our colimit. At every step of the construction, we're going to take the 2-to-1 covering map that works on exactly this principle and just stack these things as a tower. I could try to draw the next one. If I do that, then what I'll get is something that has to wrap around 4 times, like so. And now I have a bunch of self-intersections that I need to eliminate. Oh, that's way too big. Yeah. You can tell I'm really prepared for this. Let's try again. So it has to have 4 layers. So we go 1, 2, 3, 4. And then we're going to go around the back. We're just going to kind of go down. Like so. And there's some self-intersections that I have to remove, but you guys get the point. Like so. And then this next guy, same map. Now we have a 4-to-1 covering, and the image in the base space is the coset of 4Z, and so on. So here's an interesting question then. We know that we have this Galois correspondence. I'll write it on the board to remind you. What it says is that subgroups of the fundamental group of a sufficiently nice space with base points, yada yada, not going to worry about the conditions you need, correspond to covering spaces of the given space. And the way this works, you might remember, is like, well, if I take some subgroup, it's a smaller group. So what I'm doing is sort of destroying pieces of the fundamental group by popping open certain loops and constructing a space where some of the loops upstairs are no longer closed. That's what happens in our circle example here, right? This loop that goes around once, like so. Maybe I do it in a color so you can see. It goes around like this. But if I do the same thing up here, then I end up going up to the other sheet, and I'm up here now instead. So it doesn't close anymore. It's only half of a loop, and you have to sort of go around twice in order to make a closed loop. That's what's happening. This is the general procedure for constructing covering spaces. So the question then is, if I look at my chain of subgroups, then they all have the form 2 to the nz as cosets, and n is going to infinity. So it seems pretty clear then that there isn't really any space that sort of lies over this. So maybe your question is, which cover is this limit, if it exists? And how do I make sense of it? It's sort of clear that as I make this bigger and bigger, there is no subgroup on the nose called 2 to the infinity z, which could possibly be lying over this thing. And so it's not obvious to me how I should say what the limit actually is, or if it even exists. If it does, it's definitely not a covering space anymore, because there's no covering space that looks like 2 to the infinity z. That's just not a thing. So whatever we're going to do, it has to be some sort of new example that has to violate this Galois correspondence in an interesting way. So in order to give this description, first off, I claim it does exist. I wouldn't be giving this talk if there was no object called a solenoid, if it turned out it didn't exist. So what I'm going to do now is give you another description of this space, sort of help us figure out what's going on here in order to construct the space, and then we'll sort of say why it's not a covering space. And this is a sort of interesting construction, or an interesting rationale in its own right. So what we do is we think of the circle another way. Instead of thinking of the circle as like the circle, think of the circle as 0, 1, the closed interval, modulo the equivalence, where the equivalence just glues 0 to 1. And that's the only thing it does. And that's an equivalence relation. I'm sure you all see that. Then our doubling map has an interesting property. When I look at all my circles this way, then the doubling map is literally what I get when I send x to 2x. But then I have to do this mod 1. So now it's not just the angling map. It's not just an angle doubling map. It's literally a doubling map on the interval, but we're taking a remainder. And we want to know then sort of what goes on as I iterate this. Well, if I do it once, then the two pieces, the two sheets of the covering space correspond to the first half from 0 to 1/2. Together, and I guess I should worry about endpoints here, with 1/2 to 1, like so. I take 1/2, I double it, I end up in the other sheet. That's what I want. Whenever I wrap around, I want to go to the other sheet. And when I do this again, like the same sort of bisection happens. If I look at the next stage, I'm interested in the intervals from 0 to 1/4. And so on. What ends up happening is I decompose this interval into 2 to the n pieces, each that looks like I over 2 to the n, I plus 1 over 2 to the n. And I ranges over all the possible values that it needs to be to make whatever this is supposed to be work. Something like that. It's not 2 to the n minus 1, it's 2 to the n minus 1. Someone will probably yell at me in the Discord if it's like super wrong. Anyway, the point is, this construction should sort of look familiar. This sort of repeated bisection where you take something and then you want to speak about where a point is in it in terms of an infinite string of, say, choices of left or right path. Well, that's exactly the construction of the Cantor set. And not without good reason. In fact, what we're doing here is we're going to explain, at least in a moment, that the limiting object that you get is actually a space who's sort of like a covering space, but instead of being a covering space, it's what's called a fiber bundle. And the fiber over any given point will actually be a Cantor set. So what do I mean by that? First, I should tell you what a fiber bundle is. So a fiber bundle is defined by the following collection of data. Sorry, I just had a quick think there. It's defined by a total space, which is usually called E, a base space, which is sort of what the space is over. For us, this is our circle. The total space will be our solenoid. Then there's a projection map from E to B, which is a map which just maps down onto the solenoid, and it has to have the property that every point, how do I say this? Maybe I should have written in the other order, that there's also this data of a fiber, and the projection map has to have the property that pi inverse of any point is topologically the same as the fiber. And this is going to be our Cantor set. And lastly, there's a triviality condition required, which is that if I take any open set, then it has to, the inverse image of the open set has to look like the fiber across the open set. In other words, locally, fiber bundles are products, and globally, they can be more complicated. And there are lots of interesting things that one can say about this. Like, you could take a whole algebraic topology course on this. So I'm not going to try to do that in one little video. But we did talk about covering spaces. And covering spaces are an example where the fiber is a discrete space, just like some collection of points. Then this last condition is sort of like our even covering condition, because the fiber being discrete means that it's just some collection of copies of U. And in general, you can make more complicated fiber bundles, and this is going to be one. Okay, so what's going on then? Well, when we construct our solenoid, what happens is we start with a circle, and we sort of saw at the beginning what's happening as I repeat this construction, and I take these subdivisions. I want to see if I can draw a good picture of this. It's going to be kind of difficult, but at first we had our circle, and then after that we had this space that sort of had a cross to it. So maybe I draw it like this so you can really see it. This is sort of a space that lies over this with a single crossing. And then as we repeat, we produce more and more of these crossings. Let me see if I can draw this. I'm going to try my best. I'm just trying to think what's the best way to start. I have like an arc that should go like this. So it should sort of look similar, except when I get all the way back, I don't end up on the same sheet, right? It should be analogous to this. When I go around the whole thing, I end up sort of offset. So let me draw the second sheet in a different color to make it clear what's going on. And now I have to go down and around like so. And then I can repeat this process, getting more and more loops as I go. We're just sort of iterating this covering space construction. I think you can see a GIF of this. I feel like I've seen this before. Like, I don't know, try Wikipedia or something. See if you can find where a good picture, like visualization of this. Anyway, what I want you to notice is that if I look over the base and I draw this in a more reasonable looking way, like I take this loop and I make it so that it actually sort of matches up with the underlying circle a little better, and I take a particular arc, right? That arc corresponds to this pair of arcs, which in turn corresponds to 4 arcs here. I have this arc, this arc, this arc, and this arc. And as you can see, at every step, the arcs are bifurcating. That's sort of what's going on here. And so to specify a point that lies over a point in the base space in the limit suffices to choose an infinite sequence of lefts and rights. So specifying a sheet of this cover, it's not really a cover, we're going to say why in a moment, amounts to specifying an infinite sequence of choices of bifurcations. But that's the exact same thing as picking a point in the Cantor set. So this is an odd space, to say the least. Let me show you like one interesting thing about this, right? Notice that if I want to go from this blue point, or this point on the blue sheet over here, to this blue point over here, I have to run around several times, right? Like it's not enough to just go, I can go once backwards, I guess, or 3 times forwards. But if I want to go from something on the blue sheet to something on the black sheet, I have to go at least 2 times around, and that's only at this step. So as I iterate this, what we're seeing is in order to move between an adjacent sheet, every time I want to change one digit in the Cantor set representation, I have to go backwards around enough times to actually get to the point where that bifurcation happened. So in other words, the number of times you have to run around the solenoid to reach a given point depends on the number of digits in the binary representation that differ. This is called the Hamming distance. And in particular, if there are infinitely many digits that differ, which of course can happen, right? I could look at like strings that look like this, left using say a 1 to represent our choice of right bifurcation and 0 for left. And this guy, these differ everywhere in every place. Well, it turns out that actually you can't get from one of these points to the other with just a single path. Or even finitely many paths, because finitely many paths are topologically the same as one path. So these points, if I call them x and y, you cannot reach y from x with a path. This is because it would require infinitely many sheets, or infinitely many trips around, and every trip around is parameterized by a closed interval, because that's what a path is in topology. It's a map from the closed interval 0, 1 into the space. And I can take finitely many of these, and that's going to be still homeomorphic, but I can't take infinitely many of them, because it's not compact anymore. So in other words, this space, the solenoid, is not path connected. And that's a little bit strange, but it's also sort of important that this be the case, because I mean, if it was, right, if it satisfied all of the conditions, then it would have to be some element or some subgroup of Z, and we just sort of said at the beginning that that doesn't really make any sense. So something had to break somewhere. The interesting thing is that it's something so basic as path connectedness. And in fact, algebraic topology of these things is like really interesting, like sufficiently interesting and sufficiently complicated that I'm not going to bother to try to talk about it here. Um, what I'll say is that there are different kinds of homology theories that you can use to talk about solenoids. And the different homology theories are all sort of predicated on different ideas for computing algebraic invariance of the space. And they sort of all compute slightly different things, but if the spaces are sufficiently nice, then they all compute the same things, or there's a natural isomorphism between them. But that's like hilariously false for things like solenoids. Like if you're not even path connected, then these spaces are sort of more similar in spirit to things like a topologist sine curve that are connected but not path connected. And as a result, the different homology theories tell you very different things. And all of this is very interesting, but I encourage you guys to go check that out for yourself, because there's no way that I could meaningfully get into that in just this little video. So let's try to figure out then if we can do something with the Galois correspondence to figure out sort of what kind of stuff is going on here. And what we want is a notion that we're going to return to later on, so I'm not going to say too much about it now. But the idea is basically that we want to sort of complete the fundamental group, right? This is sort of very similar to what happens in real analysis. Like in analysis, you have an object like Q, and you have sequences, but the problem is that not all your sequences converge. Like there's no point in Q corresponding to the sequence of decimal approximations of any irrational number, and that's annoying. So what we need to do is sort of add things to Q to sort of fill in what's missing so that we can take reasonable limits. Well, we want to do the same sort of thing here. We want to sort of complete the fundamental group in a way so that it contains limits that are indexed by this sequence of numbers and maps between them. And this notion exists, and for us, it's called the profinite completion. And we're going to talk more about pro-objects in like chapter 6 or something of the book. So it's not important that we like get into the details of what this is, or like any theory about it for the moment. But the moral for us is that when we take the profinite completion of Z, which I'm going to define it at least for a moment, we'll obtain this new thing Z hat, and elements or subgroups of Z hat will correspond to limits of covering spaces. And we could call this our profinite Galois correspondence. So first, what we're going to do is sort of think about this business of limits in two other situations, both of which are sort of relevant and important to this conversation. So the first of which is the very famous example known as the p-adic integers. Maybe this is really example 2 because example 1 is the solenoid. But p-adic integers are relevant to solenoids in an important way. So the p-adic integers are this construction that takes the ordinary integers, and it also works by a sort of completion principle. But it's not like the usual completion, the way some of you might be familiar if you're thinking about like Q. What the p-adic integers do is they take a number, like say, I don't know, a third. We know that numbers like a third have a decimal expansion as 0.33 repeating. And we sort of understand that when this decimal expansion goes on to the right like this forever, that this is sort of an approximation or like a sequence of estimations, if I stop at any given point, that tells me what this value is. Well, the p-adic integers sort of work on a similar principle, except they also allow the expansions to go in the other direction. So this is ordinary decimals. And p-adic numbers allow us to take arbitrary sums that run from minus infinity to infinity in powers of some base, almost always a prime number. When it's not a prime number, people sometimes speak of i-adic or l-adic stuff, but we're going to deal with prime numbers, which go in both directions. And basically the question is, how do you make sense of that? And that's sort of the heart of the subject, right? That's sort of why we need this limit construction. So what we're going to do is take the inverse limit. Inverse limit? Yeah, inverse limit. Of the rings z mod p to the n z with maps between them given by just taking the remainder. Is that right? Or do I want to go the other way? I always get this confused. We're taking the inverse limit. That's the sequence of guys where we have z mod p, and then they go backwards like this. So it's multiplication. So the maps between them are multiplication by p. Okay, so then the object that gets constructed when we do this then consists of elements that sort of lie over all of these things, mapping to each of them. And there has to be a sort of suitable inclusion of all of these guys And so what we get then are sequences of numbers. I don't think this is right. I'm sorry. I'm pretty sure. I'm really thinking it should be the other way around. Let me just have a quick think. I'm sorry. I don't normally think about this thing purely categorically. Let me try just giving the definition with the ordinary language, and then we'll figure out which way it goes because we're smart. So normally the deal is a p-adic integer is a sequence an, where each an belongs to z mod p to the n z, and then whenever n is less than some other number l, then an is congruent to al. Excuse me, mod p to the n. So what's going on here is we're doing this projection every time. So like if we have a an lying over al, then we have a map which does this reduction mod p to the n. And so that means I'm taking remainders, which means what I want to do is, I think I was right, maybe I was right the first time. I think I want to go the other way. Because I'll have z mod pz, and then z mod pz, p squared z, z mod p cubed z, and so on. And if I'm at, say, the third spot, 3 is bigger than 2, so that means that if I pick any element in my sequence, then the element in the second component and the third component have to have the same equivalence class. So when I take the remainder mod p squared, I get the same thing. I'm still feeling confused here. The inverse limit is the one that points. Oh, okay, maybe I was right the first time. Maybe it does go this way. Yeah, this notation is really confusing. I'm sorry, guys. Anyway, so the point is that the collection of such sequences can be checked to satisfy this property, that it sort of lies over all of these things, given by the various truncations at each step. You just want to, if you want to map down into like p to the nz, well then you just take the representative in the nth spot, and this compatibility condition sort of forces it to be the case that these things make sense, because when I compose with the projection maps from each to the next, then that they have to lie in the same equivalence class guarantees that this is a well-defined object lying over all of these objects sort of simultaneously. Yeah, so this has got to be right. Okay, and this is an inverse limit that's been taken in the world of rings. There's another inverse limit that we should talk about, which is just the profinite completion in general. And that makes sense for groups. I guess this works for rings or for groups. Let's just think about it for, no, it needs to make sense for rings, because I need it when I'm going to talk about doing the arithmetic in this. I want to invoke the Chinese remainder theorem. Oh, but it's okay though, because modular arithmetic plays nice with multiplication. So while it's true for groups, the exact same construction works for rings, because I know just from arithmetic that introducing multiplication in z mod p to the nz is not going to change anything. And arithmetic in this sort of thing, maybe I should say a few remarks about this. Arithmetic in this sort of thing is like a little bizarre, because all the elements here look like they just deal with like sequences of positive numbers, but there are definitely things in here that like play the role of negative numbers. So like let's just suppose that p is 2. That's the case we're going to be interested in, because we're going to be thinking about p-adic stuff since we're dealing with the doubling map, and you'll see why in a moment. What this means is that if I look at an element where the tuples in the power series expansion that I wrote above are all 1s, like the coefficients are all 1s, and I add to this a number that looks like an infinite chain of zeros with a single 1 at the end. When I add this, then the 1 gets bumped up to 2, which then reaches the next power of 2, so it carries forward. And this thing propagates forward like so. And then everything cancels because the 1s just sort of run off to infinity and they're gone. If I think of this number as just being like ordinary 1, that means this infinite chain of ones here is sort of like minus 1. So this infinite expansion sort of corresponds in a loose way to a negative number. But of course, if I just tweaked this a little bit, like if I just changed some of the ones to zeros so that the carrying procedure stops, then that wouldn't happen anymore. And then some infinite numbers, some infinite expansions, just don't have a classical analog. Like they're neither positive nor negative, they're just infinite numbers. And we can sort of play a similar sort of remainder game sort of on the world of topology. Like we sort of saw this when we were dealing with like z mod 2 to the nz, when you want to think about like, or sorry, when you want to think about groups 2 to the nz and then sort of quotient groups z mod 2 to the nz, or just maybe even more generally r mod 2 to the nz. You can sort of play this same kind of take the remainder game that runs forever, and you get sort of interesting topological spaces. In fact, that's one way to construct this solenoid, is to just regard it as the limit r mod 2 to the nz. In fact, that's sort of the same thing, because I said start with the interval and glue the endpoints together, and then this sort of repeated subdivision, finer and finer, is the same thing as working with all of r, and then expanding out the lattice, sort of stretching that out. Okay, let's think about then what's going on with this profinite completion business. I should tell you what it is, at least for groups. We'll worry about what it is maybe in general when we get there, when I myself know what it is for a category. So if I have a group G, then I can look at the collection of normal subgroups, which we denote by n. And then I can form an inverse system out of this by looking at the normal subgroups and then their quotients. And then I'll have some objects that all look like quotients, G mod n. And I want to form an inverse system of this guy by just sort of looking at these quotients and looking for the universal object that lies over all of them. In general, this is a really sloppy thing to do. Like, why should this be nice? I mean, if the group is simple, then it's great because there aren't any. But in general, why should this be a nice object? In fact, it's usually not. Maybe I should write down what I'm saying. However, for Z, life is good. And the reason is because Z is, of course, abelian. So every subgroup is normal. But also, it's free. And so every subgroup is also free, or at least free abelian. And so in particular, all the subgroups are just nz for various n's. So what we're trying to do is form an inverse system where we have z, and then lying over this, I want all of the different things sort of lying over this. Oops. Sorry, I lost my pen there for a second. And then over here, I have z mod 4z lying on top of this guy. I have z mod 5z over here. And I have all these quotient maps. Or sorry, these need to run. I need to make sure I get this right. Otherwise, it doesn't really make any sense. Let's see. I want, because I can't quotient that way. Otherwise, I'm going to be in trouble. I can't send z mod 2z into z because the only way to do that would be to send it to 0. So how does this work? I take all of these groups, z mod 2z. I just need to think about what this is. I take all of these groups, z mod 2z, z mod 3z. Oh, I see. The thing doesn't include z itself. That's the problem. I only take the elements that actually appear in this thing. And then it's sort of just like the p-adic. So if I go back to the p-adics up here, then they map down. So then I have z mod 4z mapping down to this guy. And then z mod 6z lies over both of these things. And I get this interesting tree pattern given by the factorization of the composite numbers. And then I have 8 above here, like so, and then 9 here, and 10 lies over 5 and 2, and so on. You get this big, nasty tree. We didn't talk about, or at least I didn't tell you this when I was talking about inverse systems at the beginning, but there really isn't anything special about using the natural numbers to make sense of inverse systems. In fact, you can really just like take any partially ordered set that satisfies the compatibility conditions like n does. You know, like I want to be able to form commutative triangles whenever I have a pair of guys. Like if I go from I to j and j to k, there should be a unique thing from I to k making the diagram commute. And I want to form an inverse system like this, and I want to have compatibility conditions like in the p-adics, where if I follow any path, I need to get the same thing. So the elements then of this nasty inverse system should be sequences of numbers, just like for the p-adics. Elements of this inverse are sequences of residue classes. So it's like n mod 2, n mod 3, n mod 4, yada yada. This is what's lying over all of these things. Now here's the great thing about this, right? There's this theorem from algebra or number theory, maybe you guys know this theorem, I hope you do, the Chinese remainder theorem, that says if I know, if I have two coprime ideals, and I know an element's residue classes modulo those ideals, then I can actually reassemble the element from that data. And that's true in this setting too. Like, in fact, it's true just for ordinary arithmetic. Like if I know the residue classes of a number, two numbers like mod 2 and mod 3, then I know that number up to addition of the least common multiple, namely 6. That's sort of the number theoretic translation of what I just said for ideals. And we're doing this over all the numbers. And so in particular, if I know the residue class mod all the primes, then I know everything that would be available in this sequence because there's no least common multiple of all the primes. That's just everything. And therefore, the only thing that's really important about this construction in this sequence are these branches that run along the powers of the primes. So and then I have the 9 branch, and then there'd be 25, which I didn't write because it's way too big, and so on. And so if I know sort of what classes live in there, then I know everything. But notice that this infinite tuple of residue classes, well, that's spliced together then out of the branches coming from the p-adic numbers, and then some weird sort of intermediary composite guys. But we know that those composite guys are completely determined by what happens on each of the little p-adic branches coming from the factors. So what this means is that everything in this infinite branch can be determined by writing down the corresponding tuples in the p-adics. And so therefore, z hat is the product over all the prime numbers of the p-adic integers, usually denoted by z lower p. And this is our completed fundamental group. Therefore then, what element does our solenoid correspond to? Well, it would be nothing but the 2 adic integers coming from the doubling map. Okay, there's another cool thing that I'd like to talk about, just sort of in this vein, which is coming from chaos and dynamical systems. Like, maybe all this abstract nonsense, like, doesn't convince you, right? Like, you know, if you're sort of new to this, or you're new to topology, like, maybe you're, like, hearing all this, and you're like, I don't believe you, like, the solenoid is a covering space. If I just do something more clever, like, or I don't know what that Galois correspondence garbage is, I don't believe you. Well, let me show you a purely geometrical reason to think about a geometrical way to realize that this is not a covering space. This comes from dynamical systems. And a dynamical system could mean a lot of different things to a lot of different people. But for us, what it means is you have a self map of a space, and you're interested in the iterates of that self map. You want to know what is the behavior as I iterate I wrote the circle for function composition so it's not confused with power. And you want to know, like, what is the behavior of a point? Well, in dynamical systems, we have a name for what sort of characterizes chaos. There are a couple of actually different, now that I think about it, different ways of thinking about chaos. But one way of thinking about chaos, the way that I want to share with you, is called sensitive dependence on initial conditions. And what this basically says is it's sort of like a discontinuity property. F is usually assumed to be continuous for dynamical systems, but it's sort of saying that the nth iterate, while continuous, can do things that are funky. The precise definition is as follows. If I have such a function f, f is called sensitive. F is said to have sensitive dependence if there exists a delta, positive, such that for any x, there's a neighborhood n containing x. I should say there exists n containing x, and there exists a y in n such that fn of x minus fn of y, maybe I could do this in general. I want to do this in a metric space, so I should really say like dfnx, dfny. Sorry, dfnx, fny. Is bigger than delta. And the idea here is that this neighborhood is sort of like also a delta neighborhood. It's something very small. And so in other words, what this says is that nearby points are eventually scattered. So even though this thing is like continuous, the points that were originally close, if I keep iterating f, they don't stay close to each other forever. Maybe another way of saying this is the forward trajectories diverge from one another. Maybe diverge is a little bit of a loaded word. I'm not 100% sure if that makes it better or not. But we can think about this now. Our solenoid was made by an iterative process, namely this doubling map. And so, therefore, it's a perfectly reasonable dynamical system. And we talked about sort of representing the points in the solenoid as being sort of lying over the circle, being indexed by points in the Cantor set. So let's sort of see what that really means, right? Like I take a point in my circle, and I want to double the angle over and over and over again. How should I think about what this map does? So the question really then becomes, how do I study the dynamical system given by the doubling map? Maybe I'll call it f of theta equals 2 theta. As a dynamical system. And also, does this map have sensitive dependence on initial conditions? And let me first motivate this by explaining you why this is a reasonable question. If this map has sensitive dependence on initial conditions, then the space that we construct as the inverse limit cannot be a covering space. And the reason is because if I'm looking at my circle, then the definition of a covering space says that if I take any point, that there exists some small neighborhood around that point, for which the pre-image under the covering map just looks like a copy of that arc. But if the sensitive dependence, then no matter what neighborhood I pick, nearby point, I think I got the quantifier wrong. It should say for any x in n. Is that right? Maybe it's okay. No, this is okay. Sorry, don't mind me. I'm just confused. What it says is that if I pick nearby points, that these nearby points eventually get scattered from one another, and then they won't lie in sheets lying over one another anymore. So there can't be even covering. So if I convince you that we have sensitive dependence on this map, then I'll have also convinced you that the solenoid is not a covering space. So in order to do that, let's think again about the doubling map and the Cantor set. So what we're going to do is take our interval 0, 1, mod the equivalence if you like, and we write every point inside it in binary. This is a Cantor set trick, if you've seen it before. Thus, every point ever in this set looks like 0 point and then a bunch of stuff. Maybe I should actually write some stuff. Looks like A1, A2, A3, yada yada, where all the AIs are either 0 or 1. Then, what does our doubling map do? Well, if I multiply all these things by 2, then all of the 1s get doubled up to 2s, which mod 2 are 0, and then you have to carry, which pushes things forward. And if that's confusing, if it's not clear what this does, just think about what happens in decimal. If I take the decimal expansion of something and I multiply it by 10, then the effect on that is to move the decimal point. But we're only interested in 0, 1, right? Everything here is mod 1. So if I move my decimal, or my binary decimal, then I delete what follows it, because I'm not interested in that stuff anymore. Everything is mod 1. So in binary, the doubling map is just the shift map. It's in particular, it's the right shift. Of course, you have to delete also, but these expansions only run in one direction, so we don't have. That's just sort of not really part of the definition, just something that's true. So what that means then is that we can understand then distances and the effect on distances using this business of the Hamming distance. It's not really quite the Hamming distance, it's more like a weighted Hamming distance. What we do is we observe that if two numbers we're expressing 2 points in this interval in binary, their distance can be computed by looking at the places in which they disagree in binary. So what happens here is if I call like the x is some expansion in AIs and the y are some expansion in BIs, then I take AI minus BI in absolute value, and I hit it with 2 to the minus I. This is just saying if they disagree in a spot, then you pick up half a point, or some suitable power of 2 of distance. And what this means then is that our shift map is actually sort of clearly going to give us a sensitive dependence on initial conditions, because what happens is then all of these values get increased by 1, right? The i's get decreased by 1. So the 2 to the minus i's, those go up by 1. And that has the effect then of approximately doubling the distance. Maybe I should write approximately here. I just realized I had a one small concern, which is like, what if it's closer on one and further on the other in different decimal positions? I don't know if it matters. I'm going to write approximately, and I'm not going to worry about it. Because geometrically, what happens then is, as I do this doubling, points are going to end up getting their distances spread out, because 2 points have distance. Let me say it this way. dxy is less than 2 to the I if and only if xy agree in the first I places. But the shift map, as I apply that over and over and over again, I'm going to run out of places. These places are used up. And whether or not they agree anymore after that is who knows, right? Like maybe they do, maybe they don't. Some points do, some points don't. As I chew through my indices, eventually I run out of places where they're guaranteed to agree at least. And so now anything can happen. Maybe just like to show you an example. I could have like 1, 1, 1, and then 0, 1, 0, 1, and then just like stuff is happening. And then I have 1, 1, 1, 1, 0, 1, 0. These things are within 1/8 of each other because at the 1/2, 1/4, and 1/8 places they agree. But if I apply my shift map 3 times, then these 3 numbers come off, and we're left with this stuff. and these completely disagree. So after 3 shifts, there's nothing in common anymore, at least in this example, and these points are now far apart from each other, even though they were originally close. So this establishes sensitive dependence on initial conditions, and therefore the solenoid cannot be a covering space of the circle based on what we've said so far. Okay, so that's everything I wanted to say about this story about solenoids. This has been a very long thing. We're pushing an hour here, but I'm glad I did this in one take rather than, or in one video rather than in several, just because I feel like I want to get back to the good stuff. So we'll continue next time with the good stuff. We're going to talk about con extensions. I had to learn this stuff myself. I've only really encountered these things sort of in passing, and I don't really understand the full story. So hopefully this will be exciting for everybody. Okay, so if you made it this far, if you actually watched through this, I'm glad. Thanks for sticking around. I'm sorry this didn't come out last week. It's very busy being a grad student, but hopefully you guys enjoyed this, and I will see you all next time. Take it easy.